So I want you to picture something for me. Just imagine you have just purchased the absolute pinnacle of modern automotive engineering.
Okay, I'm picturing it.
Right, so it's an electric vehicle,
Mm.
brand new, fresh off the assembly line. The paint is flawless. The interior smells like, new leather. But more importantly, the engineering itself is perfect.
Well, I mean, define perfect.
I mean, literally perfect. Like the hardware is pristine, the battery cells are balanced down to the microvolt, the software code has been triple checked, triple validated. There's zero bugs anywhere, no wires are cut, no fuses are blown. By every single traditional definition of a machine, this thing is flawless.
Right, it sounds like the dream scenario, honestly.
It does, but here is the nightmare. You are driving this flawless machine on a winter road. It's icy. You take your foot off the gas pedal to coast, which is, something you've done a million times in your old gas car.
Yeah.
And suddenly, violently, the car just spins out. You're doing a full 360 on a highway.
Which is obviously terrifying.
Terrifying.
Yeah.
Or, try this one. You're on a 2-lane highway, right? You pull out to overtake a semi-truck. You floor it. You're right alongside the truck. Oncoming traffic is approaching fast, and your car just shuts down. Completely dead. No power.
Yeah. And the scariest part about both of those stories,
Right.
in neither case did the car actually break.
Exactly. And that is the mystery that we are unpacking today in this deep dive. How can a system that is working exactly as it was designed, like the code is executing perfectly, sensors are reading perfectly, how can it still try to kill you? We're moving beyond the era of my car broke and entering this weird new era of my car is confused.
It really is. It's a fundamental shift in engineering philosophy. We're talking about a concept today called SOTIF.
SOTIF. S-O-T-I-F.
Right. It stands for Safety of the Intended Functionality. Formally, if you're looking at the documentation, it's known as ISO 21448. And honestly, if you are at all interested in the future of autonomy, or even just how your current EV works sitting in your driveway, this is probably the most important standard you have never heard of.
So our mission today is to essentially tear this standard apart. We're going to look specifically at the brain of an electric vehicle, the power domain controller, or PDC, and figure out why the old safety rules just aren't cutting it anymore. But before we get to the ghosts in the machine, I have to ask, why do we even need a new standard? Because I know for a fact that automotive safety is incredibly rigorous.
Oh, absolutely. It is.
I mean, engineers have been obsessing over this stuff for decades, right? There are literal Bibles written on safety. Why aren't those old rules enough?
To really understand that, you have to look at let's call it the old world versus the new world. For a long, long time, the absolute gold standard in automotive was ISO 26262. We call it FUSA, or functional safety.
FUSA. Okay. And how rigorous are we talking with FUSA?
Extremely rigorous. I mean, FUSA uses a scale called ASEAL. That's automotive safety integrity level. If you're building, say, a steering column or an airbag controller, that is likely going to be ASIL D, which is the absolute highest level of stringency.
So what does ASIL D actually mean in practice for the person driving?
It means the probability of a dangerous failure must be less than 10 to the power of -8 per hour of operation.
Wow. That's a very small number.
It's vanishingly small. It effectively means never. It means you could drive for 1,000 lifetimes and not see a hardware failure. But here is the catch, and this is crucial to understand. FUSA is deterministic.
Deterministic, meaning what exactly?
Meaning it focuses entirely on failures. It asks very specific binary questions. Did a transistor short out? Did a bit flip in the memory bank? Did a rat chew through the brake line?
So it's looking for broken bones.
Exactly. It's completely binary. The component is either working or it is broken. And if the hardware works, FUSA basically assumes the car is safe.
Right, but going back to the scenarios I described at the start, the hardware in those cars was totally fine.
Precisely. And that is exactly where SOTIF comes in. ISO 21448, SOTIF, it deals with limitations, not failures. It asks a much harder, honestly much weirder question. What happens if the system is structurally sound, the code is bug-free, but it simply doesn't understand the environment it's in?
Ah, so it's not the system is broken, it's more like the system is incompetent.
Or the system is insufficient. There's a really great metaphor for this that engineers use. Functional safety, FUSA, is like checking your glasses. You look at the lenses, are they cracked? No. You look at the frames, are they bent? No. Okay, your glasses are safe.
Sure, they're physically intact.
Right. But SOTIF is checking your prescription.
Oh, that's good.
The glasses aren't broken, they're pristine. But if the prescription is wrong, or if they just aren't strong enough to see through a dense fog, you're still going to crash your car.
That is a really helpful distinction, because in that fog, having unbreakable glasses doesn't help you at all if you still can't distinguish a semi-truck from a tunnel entrance.
Exactly. And in the world of modern electric vehicles and autonomous systems, the fog is everywhere. We are dealing with these incredibly complex algorithms interacting with a chaotic, completely unpredictable world. We're moving from a deterministic world of if a wire cuts, then it fails, to a probabilistic world.
Okay, so if nothing is physically broken, no short circuits, no loose wires, no bad fuses, where does this danger actually come from? Like, if the machine is perfect, where exactly is the ghost hiding?
Well, in the context of the power domain controller, the PDC, which is the main computer managing the energy flow in an EV, the source material identifies four specific, let's call them roots of evil. These are the four places where SOTIF risk actually lives.
The four roots of evil. That sounds ominous. Let's walk through them. What is number one?
The first one is sensor limitations. We really have to remember that sensors, cameras, radars, wheel speed sensors, they are bound by the laws of physics. They aren't magic, and they certainly aren't human eyes.
Can you use a concrete example of how a sensor limitation creates one of these ghosts?
Yeah, let's take the icy road scenario you mentioned. You have a wheel speed sensor on the car. Its only job, its single purpose, is to count how fast the wheel is spinning and send that voltage signal back to the computer. Sounds simple, right?
Yeah, it seems completely foolproof.
But if the car is sliding wildly on black ice, that wheel might be locking and unlocking rapidly. The vibration, the erratic movement, the signal itself becomes full of noise.
Well, when you say noise, you don't mean sound, obviously.
No, I mean signal noise, voltage spikes, dirty data. The sensor isn't broken at all. It is measuring the chaos exactly as it sees it in the physical world. But if the main computer receives that messy signal and doesn't have a robust filter to smooth it out, it might suddenly think, oh, the wheel is spinning at 100 miles an hour, when the wheel is actually stopped.
So the sensor is basically a panic narrator, and the computer is just a really gullible listener.
Exactly. The sensor is just overwhelmed by the physics. That's a limitation, not a hardware failure.
Okay, that makes sense. What is the second root of evil?
Algorithm limitations. Engineers often call this the model mismatch. You have to understand that algorithms are essentially mathematical maps of the physical world, but the map is not the territory.
I saw a note in the research about the battery management system, the BMS.
Mm.
Is that where this model mismatch happens?
That's the classic case. So the BMS has to constantly guess how much power the battery can give at any exact moment. They call that the state of power, or SOP. You can't just stick a dipstick into a lithium-ion battery to see how much energy is left. You have to estimate it using a complex math model.
And math models are always based on assumptions.
Right. So imagine it's extremely cold outside, like 20 degrees below zero.
Batteries hate the cold. My phone dies instantly when I'm out skiing.
Exactly. In extreme cold, the internal resistance of the battery spikes dramatically. The actual chemical reactions slow down. But what if the BMS math model doesn't perfectly account for that specific extreme temperature curve? The math might say to the car, hey, we have 100 kilowatts of power available.
But the actual battery chemistry says, no, we don't.
Precisely. The algorithm is technically executing its code correctly. There are no bugs in the lines of code, but its understanding of reality is fundamentally wrong. It promises power that simply doesn't exist.
Wow. So we have sensors that get overwhelmed by physics and algorithms that rely on bad mathematical maps. What is number three?
Environmental uncertainty. This is often referred to as the open world problem. We design and test these cars in incredibly clean labs and perfectly paved, predictable test tracks. But the real world is messy.
And this is where that term low mu comes in, right? Because I see it all over the documentation we're looking at.
Yes. Mu is the coefficient of friction. It's a basic physics term. Sandpaper has high mu, so lots of grip. Ice has low mu, almost no grip at all.
So low mu is basically just engineer speak for really slippery.
Yeah, pretty much. But it matters immensely because code is rigid. Code likes if X, then Y. But the environment is totally fluid. If you drive from dry asphalt, which is high mu, onto a sudden patch of black ice, which is low mu, the physical reality of the car changes in literally a millisecond. If the computer system assumes high mu when it's actually low mu, you crash. That is environmental uncertainty.
Right. Okay, and the fourth root of evil. I have a feeling this one is probably my fault.
It usually is. The fourth source of risk is foreseeable misuse.
The human element.
Humans are the ultimate chaos factor in any system. We use features in ways that engineers absolutely didn't expect, but, and this is the key part of SOTIF, ways they should have predicted.
Foreseeable is the operative word there then. We aren't talking about, malicious hacking or someone trying to break the car. We're talking about basic human stupidity or laziness.
Or just simple confusion. Think about it. If you give a driver a one-pedal driving mode, where the car brakes hard the second they lift their foot off the gas, you have to foresee that a driver might use that mode on a busy highway at 70 miles per hour, suddenly get startled by something, and lift their foot off completely in a panic.
Which would effectively slam on the brakes in the middle of flowing freeway traffic.
Right. And that is not a system failure. The system did exactly what it was programmed to do. That is a user error. But under the rules of SOTIF, the engineer is responsible for baby-proofing the car against that exact human error.
So we have the 4 roots: sensors, algorithms, environment, and torus. Now, I want to see these actually play out in action. The source material outlines some absolute nightmare scenarios. And I want to go back to that first one I teased earlier, region on ice.
Nightmare scenario A, this is a big one.
I really want to slow this down because I want to make sure you and I really understand the mechanics here. So I am driving an EV. It's winter. I'm doing, let's say, 50 miles per hour.
Okay, you're cruising.
I see a squirrel dart out, or maybe a sharp curve ahead, and I lift my foot off the accelerator. Now, in my old gas car, the car would just coast. It would slowly lose speed due to air resistance and friction. No drama at all.
Right. But you're in a modern EV, and EVs have regenerative braking. To extend your driving range, the electric motor actually turns into a generator. It tries to grab the kinetic energy of the moving car and shove it back into the battery pack as electricity.
Which is usually a great thing. It saves brake pads, extends range.
It's an amazing feature. But to do that, the motor has to apply what's called negative torque. It essentially creates a strong magnetic resistance against the physical rotation of the wheels. On dry pavement, this just feels like a nice, firm, smooth brake.
But we aren't on dry pavement in this scenario. We are on black ice. Low mu.
Very low mu, maybe a friction coefficient of 0.1. That means the tires have almost zero grip on the road surface. Now, here is where the architectural conflict happens in the system. The power domain controller sees you lift your foot. It looks at its internal pedal map and says, okay, driver wants to slow down, engage region, apply 500 newton meters of negative torque immediately.
But the ice can't handle 500 newton meters of force.
Not even close. The magnetic braking force from the motor is instantly stronger than the tire's physical grip on the ice. So the wheel just stops rotating. It locks up completely.
But the car itself is still physically moving forward at 50 miles per hour.
Exactly. You are no longer driving a car. You are piloting a 2-ton sled. And because the rear wheels usually provide the bulk of that heavy regen braking, you instantly lose rear-end stability. The back of the car tries to overtake the front of the car. You spin.
And the truly terrifying part of this is that the inverter, the actual component controlling the electric motor, is doing exactly what it was told to do. It's saying, he lifted his foot, I applied the brake.
It is blindly following orders. In older EV designs, the inverter didn't check with the ABS system fast enough. It literally didn't know the wheel was locked up and skidding. It just kept applying that magnetic force.
So how does SOTIF actually fix this? Because we obviously can't just get rid of regenerative braking entirely.
No, we need it. So we need a logic shield built inside the power domain controller. SOTIF says it requires 2 main mechanisms to prevent this: slip control and a rate limiter.
Unpack slip control for us. How does that work?
The PDC has to stop acting blindly. It needs to constantly calculate the slip ratio, which engineers refer to as lambda.
Lambda. Okay, sounds like a fraternity.
Yeah, but it's just a math problem. It continuously compares the rotational speed of the wheel to the actual forward speed of the vehicle. If the wheel is spinning 20% slower than the car is actually moving across the ground, your slip ratio, your lambda, is 20%.
That seems really bad.
It is bad. The SOTIF rule says if lambda exceeds a certain safety threshold, say 15%, or if the ABS system sends out a panic signal, the PDC must intervene immediately. It has to cut the regen torque to absolutely 0.
So it just has to release the magnetic grip, just let go.
Yes. It effectively throws the electric motor into neutral so the wheels can freely spin up again and regain physical traction with the road.
And speed is the critical factor here, right? Like computational speed.
It is everything. The SOTIF documents specify that this entire communication loop has to happen in less than 10 milliseconds.
10 milliseconds. Why does it have to be so incredibly fast?
Because physics simply doesn't wait for your code to compile. If it takes 100 milliseconds for the computer to realize the wheel is locked, the car has already rotated too far. You're already sideways on the highway. The real deep dive takeaway here is that we are having to teach the energy system, the battery, and the motor to act like a dedicated safety system.
Okay, so the computer cuts the power in 10 milliseconds. The wheels catch the road again. We're pointing straight. We are safe. But now we need to bring the regen braking back right because my foot is still off the pedal.
Careful. If the computer just slams the regen back to 100% instantly, you'll just shock the tires into locking up all over again. You'll be caught in this violent loop of lock, release, lock, release.
That sounds jerky and honestly just as dangerous.
It is. That is exactly why you need the second part, the rate limiter. Imagine you're walking on a totally frozen lake. You slip, but you catch your balance. Do you immediately start sprinting again?
No way. I take a tiny, tentative step. I test the grip on the ice.
That is exactly what the rate limiter does. It forces the computer to ramp the torque up slowly. The SOTIF spec suggests increasing the torque at a rate of less than 100 newton meters per second.
That sounds pretty slow.
For a modern computer, it's agonizingly slow. It's essentially tiptoeing, but it ensures that as the magnetic power slowly comes back, the physical grip holds. It's literally teaching the machine to have situational awareness of the road.
That is just fascinating. It's not just about knowing how to stop. It's about knowing exactly how to start again safely. Okay, let's move to nightmare scenario B. You called this the overtake fail.
This one is a classic SOTIF case study because it involves a direct conflict between self-preservation of the hardware and the actual safety of the human passengers.
So paint the scene for me. I'm on a 2-lane country road. I pull out to pass a slow-moving truck. I am now in the oncoming lane. I need speed, and I need it right now. So I floored the accelerator.
Right. Now, in the background, your car's battery management system, the BMS, has done a calculation. It says, based on my mathematical model, we have 200 kilowatts of power available right now.
It's just plenty of juice to pass the truck safely.
Theoretically, yes, but let's say it's a cold day, and your battery is a few years old. The BMS makes what we call an SOP prediction error. It thinks the battery is fundamentally stronger than it actually is. So the motor controller believes the BMS, and it demands that full 200 kilowatts to accelerate the car.
So the motor asks for the check. Could the battery actually cash it?
The battery tries its hardest, but because of that internal resistance we talked about earlier, Ohm's law kicks in and the voltage completely crashes. Think of it like trying to suck a really, really thick milkshake through a tiny, flimsy paper straw. If you pull too hard, the straw just collapses on itself.
The pressure drops.
Exactly. Inside the car, the electrical voltage drops. And if it drops too low, it hits a hard limit called the undervoltage lockout, or UV low.
And what happens when it hits UVLO?
The inverter, which is the very expensive component driving the motor, sees the voltage crash and thinks, warning! We are about to permanently damage the hardware. Shut down immediately. And it completely cuts propulsion.
Whoa, wait a minute, pause. You're telling me I am in the oncoming lane, facing a semi-truck driving right at me,
Yeah.
and the car decides to just quit.
Yes.
Why in the world is protecting the hardware the priority in that moment? Like, if the inverter blows up, I'll buy a new inverter. If the car shuts down in front of an oncoming truck, I die. That seems like an incredibly terrible trade-off.
It is a terrible trade-off.
Okay.
You have to understand the fundamental physics of the electronics. If the voltage drops below that UV low threshold, the electronics literally cannot function. It's not a philosophical choice by the computer, it's physics. The transistors will simply fail to switch. The car stops whether the software wants it to or not.
So it's not actually a decision the car is making, it's just a structural collapse.
In the old system design, yes. It's a hard failure. A brick wall.
Okay, so how do we fix that under SOTIF? How do we keep the car moving when I need it most?
SOTIF introduces a concept called the voltage closed loop. It acts as a sort of survival instinct for the car. Instead of just blindly trusting the BMS prediction, the system monitors the actual live voltage in real time.
Trust but verify.
Exactly. As the motor pulls power to pass the truck, the PDC watches that voltage line like a hawk. If it sees the voltage starting to dip dangerously close to that UVLO death limit, it intervenes before the crash happens.
What does it actually do to intervene?
It actively reduces the driver's request.
There you go.
Essentially says to the motor, okay, we cannot do 200 kilowatts right now, but we can safely do 150. It automatically backs off the throttle for you.
This is what the SOTIF documents call graceful degradation.
I love that term so much. Graceful degradation. Instead of a hard failure where you completely stop in oncoming traffic, you get a power reduction. Your acceleration slows down a little bit, but crucially, you keep moving forward. You can still complete the pass or safely tuck back in behind the truck. You don't just become a sitting duck.
graceful degradation sounds like a really good life goal, honestly. But in engineering, it literally saves lives. It turns a total loss of propulsion into just slightly less propulsion.
And that distinction is the entire point of SOTIF. It's about managing the limitation of the machine so it becomes an annoyance, not a fatality.
Okay, let's quickly touch on scenario C and D from the outline.
Hmm.
Scenario C involves torque vectoring.
Right. Torque vectoring is an advanced feature where the car uses two separate electric motors to help steer the car. You power the outside wheels slightly more to help the car turn sharper into a corner.
Sort of like how a tank turns by powering one pred more than the other.
Exactly like a tank. But this whole system relies heavily on a yaw rate sensor.
Yeah.
Mhm.
That's the rotation around the vertical axis, like spinning like a top.
Correct. Now, these tiny sensors can drift over time, especially with rapid temperature changes. Imagine you're driving, and the sensor drifts and suddenly tells the car's brain, hey, we aren't turning enough for this corner, when you actually are turning perfectly fine.
So the car thinks it needs to help me turn more than I am.
Right. It decides to fix the imaginary problem by adding a huge amount of torque to one side of the car. This leads to what they call unexpected yaw. The car basically steers itself right off the road because it's aggressively chasing a sensor error.
That sounds like a demonic possession. The car just yanks the wheel out of your hands.
Yeah.
So what is the fix for that?
Authority limits. This is a concept that actually goes all the way back to the unintended acceleration issues of past decades. You put a physical cap, a hard-coded limit, on exactly how much the computer is allowed to intervene.
So it puts a leash on the computer.
A very short leash. For example, the system architecture might dictate the maximum difference in torque between the left and right wheels can never, under any circumstance, exceed 500 Newton meters. Even if the deep learning algorithm thinks you desperately need 1,000 Newton meters to fix the turn, the authority limit steps in and says, no, 500 is the absolute max. I don't care what your math says.
And the logic there is simply that the human driver's steering input at the physical wheel must always win.
Always. The computer is designed to be a co-pilot. It should never be physically strong enough to wrestle control of the car away from the human being.
And finally, we have scenario D. The one-pedal misuse. We touched on this earlier, the panic lifting situation.
The specific hazard here is actually about the people driving behind you. If you completely lift off the accelerator in one-pedal mode, the EV decelerates at maybe 0.2 G or 0.3 G of force. That feels exactly like slamming on the physical brakes to anyone in the car.
But because I didn't actually touch the physical brake pedal with my foot.
Right, in older system designs, the brake lights on the back of the car might not even turn on.
Whoa. So I am effectively panic braking in the middle of the highway, but to the guy doing 70 behind me, it looks like I'm just casually coasting.
Yep. Until his front bumper hits your rear bumper, that's a massive rear-end collision risk. So the SOTIF solution here is a hard, non-negotiable rule. Auto brake lights. If the deceleration force of the vehicle exceeds 1.3 meters per second squared, the computer must turn on the brake lights.
Even if my foot is nowhere near the brake pedal.
It absolutely doesn't matter what your foot is doing. It only matters what the physical mass of the car is doing. SOTIF demands that the car accurately reflect its physical reality to the outside world.
Okay, so we have thoroughly covered the specific mechanical nightmares, but I want to zoom out a bit. We've been talking about fixing known problems, but what about the problems we don't even know about yet?
Yeah, that is by far the hardest part of all this.
There's this mental model in the research that's called the SOTIF 4 quadrants. It sounds kind of like a corporate business school matrix, but for, surviving your commute.
It's actually a fantastic visual tool. Just imagine a standard square divided into 4 distinct boxes. The axes of the graph are known versus unknown and safe versus unsafe.
Okay, walk us through the 4 boxes.
Area 1 is known safe. This is a bright sunny day on a straight highway. The system works perfectly and we fully know it works. This is where we want the car to be 99% of the time.
Easy enough. What about area 2?
Area 2 is known unsafe. These are the bugs and limitations we already know about. For example, we know for a fact that the front-facing camera will go temporarily blind when you exit a dark tunnel directly into bright, blinding sunlight.
So we know it's a structural problem.
Yes. And specifically because we know it's a problem, we can write code to handle it safely. We write logic that says, if the camera is sun-blinded, maintain current steering angle and loudly warn the driver to take over. We can actively manage Area 2.
Then there is Area 4, skipping ahead, unknown safe.
Right, Area 4 is the stuff we didn't explicitly plan for in the lab, but the car somehow handles it safely anyway, either by pure luck or just really robust general design. Engineers don't worry too much about Area 4.
Which leaves Area 3, the unknown unsafe.
Yeah, the danger zone. The unknown knowns.
The things we haven't even thought of yet.
Yeah. Exactly. The completely weird combination of, say, a specific low angle of the winter sun, plus a specific type of highly reflective silver truck, plus a weird patch of wet oil on the road that specifically confuses the radar waves. We don't even know this bizarre scenario exists yet, so we obviously can't write safety code for it. And because it's intrinsically unsafe, it causes unpredictable accidents.
So the entire overarching goal of the sort of standard is to shrink Area 3.
The goal is to aggressively drain Area 3 into Area 2. We want to actively discover those unknown bugs in the lab so they become known bugs, because once they are known bugs, we can engineer a fix for them.
But how do you actually find a ghost that you can't even see? You can't just drive around waiting to crash to find out what happens.
You're right, you can't just test drive a billion miles in the real world. It takes way too long and it's too dangerous. So engineers use some very clever techniques. One major one is called STPA, or System Theoretic Process Analysis.
That is definitely a mouthful.
It is a mouthful. But it represents a total shift in thinking. Instead of looking for broken physical parts, STPA looks for unsafe control actions, or UCAs.
Give me a real-world example of a UCA.
Okay, so instead of a FUSA engineer asking, did the brake line physically cut in half, an STPA engineer asks, did the computer apply the brakes too late? Or did it apply the brakes too much for the current traction?
Ah, I see. It focuses entirely on the behavior of the system, not the physical component itself.
Right. Applying too much regen torque on a patch of ice is a classic UCA. We identify that dangerous behavior first, theoretically, and then we work backward through the code to find out why the computer might falsely decide to do that. It's really like detective work for logic.
But at the end of the day, we still need to actually test this stuff, right? We
Yeah.
can't just sit in a room and theorize forever.
True. And that brings us to simulation and parameter sweep. We use massive, incredibly powerful supercomputers to run what are called Monte Carlo simulations.
Like the casino.
Exactly like the casino. We roll the dice over and over. We run literally millions of virtual test drives. In one simulation, the virtual road is totally dry. In the next fraction of a second, the road is wet. Then it's icy. Then it's icy and the virtual battery is heavily aged. Then it's icy, the battery is old, and the tire pressure is randomly low.
You are just randomizing the entire world to see what breaks.
We are sweeping through every possible parameter to find the exact weird 1 in a million combination where the steering algorithm finally fails. We want to find that edge case inside the supercomputer so we don't accidentally find it on a real highway with a real family in the car.
The document also mentions HL rigs, hardware in the loop. What does a HL rig actually look like in a lab?
Oh, HL rigs are extremely cool. Imagine a large, sterile room. In the center of the room is the metal chassis of a car, or sometimes just the bare electronics laid out on a table. No wheels, no body panels, just the digital brain and the wiring harness. And it's hooked up to a massive supercomputer.
Okay, ideally not a matrix situation where it becomes sentient.
Kind of like the Matrix. The supercomputer is constantly feeding the car's brain completely fake sensor data. It says, here is a digital picture of a stop sign. Here's a simulated radar bounce of a truck. The car's computer genuinely thinks it is driving downtown in Tokyo. It thinks it's moving. It activates the physical inverter and fires signals to components that aren't there.
And we can purposefully inject noise into this matrix simulation too.
Exactly. This is called noise injection. We don't just send a perfectly clean digital signal. We intentionally send a signal that looks like a camera sensor actively failing. We add static interference. We artificially delay the radar signal by 5 milliseconds. We are actively trying to see if the car's brain panics under stress.
It's basically stress testing the internal logic. But surely, even with all that, nothing beats actual real-world driving.
Nothing does. The real world is infinitely complex. But we obviously can't risk human lives testing experimental safety code on public roads, so we use shadow mode.
This is honestly one of my favorite concepts from the research. Shadow mode. It sounds like a covert spy movie operation.
It is the ultimate real-world test lab. Imagine you are an automaker and you have a fleet of 100,000 customer cars driving on the road right now. You have just developed a brand new, highly experimental algorithm for handling regen braking on black ice, but you definitely don't want to give it actual control of the brakes yet.
Way too risky. What if there's a bug?
Exactly. So you push the code out via an over-the-air update, and you deploy it in shadow mode. The new code runs silently in the background on those 100,000 customer cars. It actively processes the real sensor data from the road. It digitally decides what it would do in every situation, but it doesn't actually have physical access to the brakes or steering. It just silently logs its decisions in a hidden file.
Just writing down, I would have slammed the brakes here.
Exactly. Then the automaker engineers pull that data back. They compare what the shadow mode algorithm wanted to do against what the actual human driver really did in that moment. If the human driver smoothly navigated the corner but the shadow mode algorithm falsely wanted to slam on the brakes, you instantly know your new code has a fatal SOTIF bug.
And you find that bug out without the car ever actually slamming the brakes on a real road. You mathematically validate the safety without taking any of the physical risk. That is absolutely brilliant.
It's revolutionary. It allows automakers to gain literally billions of miles of real-world testing experience in a matter of weeks, completely safely.
Okay, before we completely wrap up this deep dive, we need to talk about what I call the eyes of the beast, the perception systems themselves. We spent a lot of time talking about the internal brain logic, but what about the actual sensors feeding it? We have cameras, radar, and LiDAR. Why does the SOTIF standard struggle so much with them?
Mostly because each one of those sensors has a very specific kryptonite, a fundamental physical weakness that you just can't code away. Take LiDAR, for instance. It uses millions of laser pulses to map the physical world in high-definition 3D. It's an amazing piece of tech, but it hates fog and heavy rain. The tiny water droplets physically scatter the laser light before it bounces back. It's exactly like turning on your high-beam headlights in a dense snowstorm. The camera just sees a blinding wall of white scatter. Also, surprisingly enough, LiDAR really struggles with black cars.
Black cars? Really? Why?
Because certain types of dark automotive paint actively absorb the infrared light spectrum. To a LiDAR laser pulse, a perfectly polished black car might look like an empty void. It literally absorbs the laser pulse instead of bouncing it back to the sensor. SOTIF classifies that as a functional insufficiency.
That seems like a pretty major problem if you're relying on it to not hit a black sedan at an intersection. What about radar then? Radar is supposed to be the one that is totally immune to bad weather.
And it is. Radar punches right through dense fog and rain like it's not even there. But radar data is incredibly messy to process. It suffers terribly from something called multipath reflections. Imagine you are driving your EV inside a metal-lined tunnel. The radar wave fires out from the front bumper, hits a car ahead of you, bounces off the curved tunnel wall, bounces off the ceiling, and then finally comes back to your receiver.
So it's an echo.
It is a totally distorted echo. Based on the extra time it took that wave to return after bouncing around, your car's brain might think the object is much further away than it really is. Or worse, it might see a phantom ghost object floating 20 feet in the air or buried under the asphalt.
That's terrifying. And what about standard cameras?
Cameras are just like human eyes. They absolutely hate high dynamic contrast. Driving out of a pitch-black parking garage directly into blinding afternoon sunlight, the camera feed just washes out completely white for a critical half-second. And then, beyond the hardware, there is the overarching AI problem.
Deep learning, neural networks.
Right. We use advanced neural networks to process the camera feeds and identify objects on the road. But neural networks are fundamentally black boxes. We feed them millions of images, they train themselves, and they learn to recognize patterns. But they aggressively struggle with something called out-of-distribution data, or OD.
Can you give me an OD example that I might encounter?
Sure. If you train an AI system on millions and millions of pictures of normal pedestrians walking down a sidewalk, it knows exactly what a human person looks like. 2 arms, 2 legs, walking upright at 3 miles per hour. But what happens if a person decides to walk out into the crosswalk wearing a giant inflatable T-Rex dinosaur costume?
Oh man, I've seen those videos. They are hilarious.
To a human, yes, they are funny. But to an AI vision system, that is a terrifying, completely unidentifiable monster. It has literally never seen it in its training data. It is completely out of distribution. The AI might classify the dinosaur as a box truck, or a weirdly shaped bush, or it might just filter it out as nothing at all. Or it might randomly predict the dinosaur is going to accelerate to 60 miles per hour like a car. That total computational unpredictability is a massive SOTIF risk.
So hearing all of this, with all these inherent physical flaws, blind lasers, confused echoing radars, AI getting totally stumped by a dinosaur costume, can we ever realistically make an autonomous car 100% safe?
No.
Wow, that was very quick, very definitive answer.
Because it's the honest engineering answer. We cannot mathematically eliminate all risk from a moving vehicle. The ultimate goal of the SOTIF standard isn't total perfection. The goal is ALAR, ALARP, as low as reasonably practicable.
Okay, so how do we as a society measure what is safe enough to put on the road?
There is a core ethical concept called positive risk balance. This is the ultimate moral calculation we have to make. The highly automated system might accidentally cause brand new types of weird, unpredictable accidents, like slamming on the brakes for an empty soda can on the highway because the radar mistakenly thought it was a dense boulder.
Which is obviously a bad thing.
It's a very bad thing. But if that exact same automated system completely eliminates drunk driving, tired driving, and people texting while driving, it is statistically guaranteed to save far more human lives overall.
So even if the computer makes completely new robotic mistakes that a human would never make, if the total societal body count goes down significantly, it's considered an acceptable win.
That is the harsh reality of positive risk balance. It is a very hard pill to swallow, especially if you happen to be the unfortunate victim of the one weird robotic accident. But for society as a whole, it is the only viable path forward for the technology.
Is a really heavy calculus. It sounds to me like we need a protective shield made of more than just one single layer of safety standards.
We absolutely do. In the industry, we call it the 3-in-1 shield. You need functional safety, ISO 26262, to ensure that the physical hardware doesn't break down. Then you need SOTIF, ISO 21448, to ensure the complex algorithms don't get confused by the environment. And lastly, you need cybersecurity, ISO 21434.
To stop the malicious hackers from taking over the steering wheel.
Exactly. Physical hardware reliability, advanced algorithmic intelligence, and robust digital hacker protection. You absolutely need all three legs of that stool to fully trust the machine with your life.
Man, this has been an incredible journey today. We started this session talking about a mechanically perfect car spinning out on a patch of ice, and we have somehow ended up discussing the deep ethics of robotic risk and the trolley problem.
It really just highlights how profoundly automotive engineering has fundamentally changed in the last decade. We aren't just mechanics turning wrenches anymore. Engineers are essentially acting as philosophers, statisticians, and psychologists for artificial machine brains.
To kind of recap everything for you listening, we have actively moved from an era of broken mechanical parts to an era of profoundly confused software algorithms. We learned today that the ghost in the machine isn't some supernatural spirit. It's usually just a rigid limitation of physical sensors or a blind spot in the training code.
And we also learned that adequately fixing those blind spots requires a lot of engineering humility. We have to openly admit that we simply cannot foresee every possible crazy real-world scenario. We have to respect Area 3. So we have to build logic systems that are inherently robust enough to safely handle the unknown. We actively teach the car to monitor its own tire slip, double-check its own internal electrical voltage, and even second-guess its own human driver if they panic.
Well, the next time you see one of those fancy EVs silently gliding down the street, just try to remember the literally millions of Monte Carlo simulations and the hundreds of thousands of lines of hidden code working silently in the background just to keep that car from getting fatally confused by a patch of black ice or a discarded soda can. It definitely makes you appreciate the engineering behind the ride a little bit more.
It certainly does for me every time I get behind the wheel.
Thanks for diving so deep into the matrix with us today. Keep questioning the machine, stay curious, and we will catch you in the next deep dive.